Today's video presentation will be a brief description and overview of a DC power plant for my tiny little central office. I've been very hesitant about producing any videos for power related issues. This is something to be taken very serious. The power plant that I have is set up identical to a real telephone company power plant, except for this is a very tiny power plant. I do have computer UPS batteries instead of the typical flooded batteries that you would find in a central office. And you can do YouTube searches and find where there's been other people who put up battery plants of real large COs. The central office that I worked in had two power plants that were approximately 1,500 amps each. One power plant carried the switch and the other one carried the load of the transport and subscriber carrier. The batteries are big, the rectifiers are big, and of course the loads were large. I've been in central offices that were very large that had incredibly huge DC power plants and were very large amp capable power plants. When working on any type of a power system that has batteries, there are the fused side and the non-fused side, which would be typically the load. This is something that I do not recommend if you have no power experience, even considering touching. Things can go terribly wrong very fast and you can have some potentially fatal results. At this point I have the number 3 crosswire switching system on, the Western Electric step switch, a North Electric CX100, and a Stromberg Carlson XY, in addition to some auxiliary loads for channel banks and SF signaling units. The brown units that we're looking at are Northern Telecom MPR25 rectifiers. From what I have been told is these rectifiers were intended to be used out at remotes such as Slick 96's, DMS Urbans, and so forth. A normal central office power plant has a lot of telemetry monitoring capabilities, and these rectifiers are plugged into a shelf that is just as dumb as a box of rocks. And I will be replacing this in the future with a more modern power plant. When I originally began building this, the only rectifier I had was a Lorraine 100 amp rectifier, which is directly below. And that rectifier weighs about 300 pounds. The MPR25s, of course, do not weigh anything like that at all. They're probably about 15 pounds apiece. I will show the cabling on the rear of the MPR25s that is connected to what would be classified as a power distribution. Then that would feed to what is referred to as a BDFB. Most of my fuse blocks were removed from BDFBs. I do have some high amp output fuses, as well as a lot of 30 amp and less. In this building, almost everything I have is way under amped from what they would normally specify in a regular office. My loads are very well thought out, and there's no one particular fuse carrying very much traffic, and that was not an accident. It was additional work to do this, but I wanted protection more than just trying to be exactly correct. The way the DC power system works in a telephone central office is the rectifiers are carrying the load of the office while there's AC power. The rectifiers are wired in parallel to the batteries. So if there is a commercial power failure, the switching equipment will not see a transition such as like on a computer UPS where you switch from the line to the battery. The batteries just simply pick up the load. Under normal commercial power situation, most of the North American power plants operate on negative 48 volts if there's no commercial power, and that is to be sustained for a long period of time, several hours. Or when there is commercial power available, we're generally floating the batteries around 52.4, 52.5, depending on the specifications of the local telco. In my case, I am set at 52.4 volts. With the rectifiers being wired in parallel with the batteries, there is no fusing between the rectifiers and the batteries. The rectifiers have an internal fuse, but between the bus of the rectifier shelf and the batteries, there is no fusing. This is exactly how it's done in a conventional Bell and independent CO. Then from the batteries or the rectifier, wherever the power is spliced together, generally at a bus bar, then they have feeds from the bus bar to high amp circuit breakers or fuses that distribute the load to what is referred to as a BDFB, and that's a battery fuse distribution board. And they can be anywhere from 30 amps up to 1,000 amps or so, depending on the office. I've installed equipment in buildings that had 1,000 amp BDFBs, lots of them, and when you're working in the rear of those, of course it's all maintenance window work. You're working in a power system that's got 1,000 amp potential, which if you ever make a mistake, you have an explosion, you weld things, start fires, bad situation within milliseconds. In this particular case, I have my fuses above the rectifier, and I will show those, and all of the different switching systems and miscellaneous fuse panels are in that. The lowest of the fuse panels, right above the 70 type fuses, which is the little wires, 22 gauge, I have 3 fuses that are the distribution to the other fuse panels located in the same relay rack. Because I have a 9-foot tall office, this is all on the top of the relay rack, so I'm recording this video on top of the ladder. I can individually remove the power from 8 circuits at one time by taking out the big fuses. The big fuses are set up for approximately 30 amp loads, I believe, and then the remaining circuits are 5 to 10, 15 amps, depending on what they're actually connected to. The very top fuse panel, the very left 2 conductors are feed to the number 3 crossbar, and then the other conductors are feed to filters and miscellaneous fuse panels. The main output from my Northern Telecom MPR25s is connected to one of these lever type circuit breakers. These circuit breakers are at least 100 amp up, so they provide no protection in my setup. The only thing that is happening here is I have this setup so I can kill the entire office with one switch, due to the fact that sometimes I'm gone for extended periods of time and my wife may have to have the ability to turn something off. I also can trip these circuit breakers remotely, and that is a circuitry setup so an overcurrent situation or an extended power outage would turn off the load to protect my batteries because they're very small batteries. I will show the rear of this panel. This is mounted in my Stromberg XY power distribution board, and this would not typically be in a setup like this in a real central office. In a normal real central office, there's no provision to turn the entire office off at any one time. Maybe a little tiny baby office you could do that, but larger offices do not have a master disconnect. Here's the rear of the master disconnect, and also circuit breakers for the XY to the different frames in the XY switching system. And then this is the big bus for the entire office. Those are live 48 volts from the battery, the rectifier. This is one of two distribution for the number 3 crossbar switching system. Here is the second setup for the number 3 crossbar. The rear of the first crossbar distribution. The rear of the second crossbar distribution. There are 2 clusters of filters. These capacitors are 35,000 microfarads for each individual capacitor, and there are 10 of them on the left and 10 of them on the right. I only have half of that bank wired up. This panel was removed from a number 1 ESS switching system, and I've used it to help filter out the noise in the power plant, and it works exceptionally well. Front view of the 70 type fuse panel. In your large central offices, step-by-step XY and crossbar switching systems, generally they would have one main fuse for the entire aisle, and all of the secondary fuse panels would be tapped into that one particular lead, and it may be fused at 300, 400, 600 amps depending on how long the aisle was and how much equipment was in that aisle. They no longer do that in any of the modern central offices. Every relay rack, or bay as it's referred, has its own BDFB fuse. So in this case that I built, I have an individual fuse for every single relay rack. When I bought this office from Nevada Bell, there was, I believe, a MCM 350 that ran across the tops of the back of the base, and then they frankled on to that lead with number 6s, number 8, and in some cases number 4 gauge wire that went to the fuse panel. Fortunately, I was involved in some tear-outs that the company I worked for allowed me to have a little bit of the cable, so I ended up with enough to fuse these. Because this is a very small office, the runs were not very long. This is some of the miscellaneous fuses in the number 3 crossbar. Unlike step-by-step, crossbar switching systems use 48 volt battery feed for the dial tone, busy, and reorder, in addition to a few other things, so that if one of the originating registers have troubles, it'll blow a fuse and bring in an alarm. In your step-by-step offices, they did not use fuses on any of the tones. You would just simply cause a massive problem in the office until you found a short. Here's also several hundred resistance lamps, and these are connected to individual trunks so that if a trunk has a problem, the light will light up. Under normal circumstances, these should never light. This is the original ringing, tone, and interrupter plant for the number 3 crossbar. This was made by Lorraine for Western Electric. This was a packaged central office, so this ringing and tone plant could be found in a small 5A crossbar office or the number 3 crossbar office. This plant is almost identical to a 806 ringing plant in a step-by-step, except this is solid state and it draws 10 amps of power in the idle mode just for the relays to operate, and I could not afford to run this, so I built a circuit interface to my to my step-by-step switching system. This is a working plant. I've had it on and it did run the office during the time I was putting it back together. If I ever get my automatic electric step switch wired up, here's the power for the AE step system. These fuse panels are the 19-teens up to the 1940s type fuses. Rear view of the number 3 crossbar system. There are 4 aisles, and this is 2 of the 4 aisles. The 2 relay racks on the right here is interrupter, tone, ringing, and power distribution for the XY, with the exception of the main emergency shutoff breakers. I'm showing some of the cabling, and these are the feeds to the number 3 crossbar. They are on the bottom side of the cable rack because you're not supposed to mix high load power with switchboard. You can have power and switchboard cables that's 30 amps and less mixed together, but anything more than that needs to be on their own cable rack or hangers. This is the distribution for small loads in step-by-step. This relay rack also has the ringing and tone in it, and the distribution for that. Sarah at the Connections Museum has done a fantastic video on ringing, and I will let her continue to do an outstanding job in the ringing. She has a power plant similar to mine, and they have better lighting for their power plant, and she does a far better job in explanations than I do. Here is the central office ground bar. And this relay rack has my little tiny baby batteries in it. A normal central office would not have batteries like this. This would be equivalent to a AAA cell in a normal central office. The flooded batteries that's found in a normal central office are about 2.17 volts. These are 12 volts per battery, so I have my 48 volts. They work just as well, but they're tiny compared to a regular CO battery. A little bonus video. We're looking at the number 3 crossbar maintenance control center, where we have the lights and the buttons and so forth. Then to the right of that is the combination marker that sets up the dial tone connection as well as completes the call. And if the call is outside of the crossbar, then it moves the information to an outgoing sender. Here is one of the fuse panels on a selector shelf in the step office. There are 6 selector shelves on one number 6 gauge power cable that then goes to an individual fuse block over in my power distribution. Back in the day that the step-by-step machines were put in, it was common practice to have a high load for multiple switch frames, and then they would tap down to a smaller lead, normally a 6 gauge, that would then be tapped down to a 10 gauge that would connect to the fuse panels. The end of the video.